Hello students, welcome to the lecture on nanotechnology. Myself, Senjo Manuel, Department of Mechanical Engineering, Characterization School of Engineering and Technology. So, in this lecture, we will go through different characterization techniques of nanomaterials. Previously, we have studied different characterization techniques such as scanning probe microscope, scanning electron microscope, X-ray diffraction, etc. Now, in this lecture, we will go through the spectroscopic technique which is used to find out the chemical composition of the specimen which you are taking into consideration. The spectroscopy is defined as the study of interaction of electromagnetic radiations with a corresponding matter. The way in which it interacts, the interaction is being studied for understanding what will be the chemical composition of the system. Now, in spectroscopic technique, the light, which is an electromagnetic radiation, it will be split into its constituent wavelengths. It is similar to in the case of, if you take the case of prism, and if you subtend light on that one, it will be splitting it in the form of rainbows of lights, different wavelengths, lights of different wavelengths. So an interaction of matter with respect to the electromagnetic radiation will be giving you a spectrum of details. That spectrum of details is being studied in spectroscopy in order to understand what will be the image that you get, or what will be the chemical composition of the systems. The nature of interaction between the electromagnetic radiation and the matter will be classified mainly into three cases. First one is absorption, second case is emission, and the third one is scattering. So by studying the absorption, there are different spectroscopic techniques where we will be studying absorption. There are some of the spectroscopic techniques where we will be studying the emissions, and there are spectroscopic techniques where we will be using the scattered light for understanding what will be the chemical composition of the system. So here the basic working principle behind that one is being shown here. You will be having a light source. It will be any electromagnetic radiation. We are having a wide spectrum of electromagnetic radiation. Any type of electromagnetic radiation is being interacted with the sample, and there will be some interaction between them, and that interaction is being dictated on a dictator, and by using the way in which the data is being transmitted from here, we will be transforming that one into the image that we require. Okay, we'll go in detail on different types of spectroscopic technique, and from there we will understand how it works. So here we are having a wide spectrum of electromagnetic radiations ranging from gamma rays, X-rays, UV, IR, microwave till long radio waves, which varies with respect to the wavelength. Now the interaction of this electromagnetic radiation is different for each class of wavelength. In our day-to-day life, the interaction that we are seeing is only coming across the visible ray region, which is at a smaller level. We are actually seeing the interaction of electromagnetic radiation with respect to the matter only in a small range, ranging from 4 nanometers to 700 nanometers. Wavelength electromagnetic waves is being the interaction of this electromagnetic is being seen in day-to-day life. Other than this, the interaction of different rays on the matter will be different in different classes of electromagnetic radiation. Say some of the examples is, if you take the gamma rays, there the influence that happens in the nuclear level. Say for example, if you take nuclear reactions, the emission of gamma rays exists. This reverse also can exist when and gamma rays is being interacted with respect to matter. A nuclear level fluctuations happens. So that has been studied in spectroscopy when we are interacting gamma rays with respect to the matter. Next we are taking X-rays. Now this X-rays will be making variations in the core level electrons. We have studied this one in electron microscopy, scanning electron microscopy, where we will be obtaining X-rays when and stream of electromagnetic electrons is being impinged on the matter, and if this electrons is being colliding, impinging or bombarding on a core electron, that is, if you take the case of K shells, the electrons in K shells, it will be ejecting out the electrons available in K shells, which is called as secondary electrons. And when this secondary electrons is ejected out, there will be a vacancy available in the K shells. In order to fill the vacancies, the electron in just higher adjacent level, that is L shell, from the L shell, the electrons will be filling the vacancy in the K shell. Now the energy level of electrons in the L shell will be higher than that of energy level available in K shell. So when it is moving from higher energy state to lower energy state, and electromagnetic radiation will be ejected out in the form of X-rays. By studying this X-rays, we can understand what will be the structure that is been obtained. So this was what we are used in scanning electron microscope. Similar to that, when X-rays is been interacting with respect to the matter, there will be variation in the core level electrons. Now the interaction of ultraviolet and visible rays will be happening in the valence electron range. So one of the example, invisible rays, the way in which the valence electron varies is been the different interaction available in our day-to-day life. The optical properties, the electrical properties, all are due to the interaction with the valence electron. Now the next one is infrared range. There are a variation, since here you can see actually gamma rays is having higher energy. As you go down, X-rays it is having much more less energy. Ultraviolet it is having much more less energy. Visual rays is also having much less energy. As the energy reduces, the wave interaction is entirely different. In infrared, it will be interacting with the molecular vibrations, and there will be variation in the molecular vibration that you obtain. Then we will be having microwave, where we will be having, instead of vibration, it will be influencing the molecular level rotation and electron spin, and the radio waves will be varying the nuclear spin. So these are some of the influencing parameter, and the way in which this influencing parameter has been studied in spectroscopy. We will go in detail on how different things influence in the different ways. So as I already explained, very energetic UVs and X-rays may cause electron to eject out from the molecules. The radiation in infrared region spectrum have much less energy. They causes vibration in molecules. When you go down much more, if you go down, the microwave radiation is even less energetic than infrared, which is neither inducing an electronic transition, that is ejection of electrons, and a variation in electronic state in molecules. Neither it will be changing the vibration, but it will be changing the way in which the molecules rotate. So this interaction has been each of the cases. So these are the commonly used type of spectroscopical techniques: ultraviolet and visible light, which varies the electronic transition; infrared, which influences the molecular vibration; microwaves, which influences the molecular rotation. By studying this, we can understand the composition of the system. As I already explained, when the electromagnetic waves interact with the matter, there are three different options that is been possible. Either it may be absorbed, either there may be scattering, either there will be emission. Based on that, you can see different examples of spectroscopical technique. One of the example of absorption spectroscopy is infrared spectroscopy. One of the example of scattering spectroscopy is Raman spectroscopy, and one of the example of emission spectroscopy is atomic emission spectroscopy. Now, in this lecture, we will go on detail on these two techniques: infrared spectroscopy and Raman spectroscopy. So, I was already explained. We will understand what is the basic working principle behind the spectroscopical technique, which you all explained in the previous phase. In absorption spectroscopy, and the electromagnetic radiation is absorbed by the atom, which undergoes transition from a lower energy state to higher energy state. This absorption is being studied. The absorption occurs when the energy of radiation matches with the energy difference between the two different levels. This absorption rate is being studied in absorption spectroscopy. But when you're taking the scattering spectroscopy, we'll measure the physical properties that is being obtained when a certain amount of light is being scattered by the interaction of light with respect to the matter. When light interacts with the matter, some of the wavelengths is being scattered out. This is being this variation in the scattered light is being studied in scattering spectroscopy. One of the important techniques that is being used for finding out the chemical composition is Raman spectroscopy, which we will go in detail. Last one is emission spectroscopy. Similar to the previous case, atoms that are in excited state will be coming back by emitting radiations, and this is being studied in the case of emission spectroscopy. So the emission can be induced by external sources such as flame or electromagnetic radiation. So this is being studied in emission spectroscopy. We are actually not going in detail on emission spectroscopy. We are going in detail on absorption spectroscopy and scattering spectroscopy, which is available in our syllabus.
Okay, next we will go through infrared spectroscopy. So infrared spectroscopy, as the name indicates, it deals with interaction of the matter with respect to electromagnetic waves which are in the infrared region. Usually these lights have longer wavelength and lower frequency compared to visible lights. So in this spectroscopy we will study how the interaction of the different molecules interacts with infrared spectroscopy, infrared lights. So in the previous phase we have learned how the different interaction comes for different classes of electromagnetic waves. So in infrared spectroscopy, the interaction of infrared rays with respect to the matter will be dealing with the vibrations of the molecules. So molecules, if you assume molecules as it's similar to a model of a vibration model where you are having a mass and the spring system. If you are taking the molecules, we can assume that one has mass and the bond between the molecules, if I am taking it as the spring, then the spring mass system, the way in which the spring mass system works, it's similar to what happens for molecules and the bond between them. So the bond between them will be in continuous vibration. Now in infrared spectroscopy, it's mainly used for determining different types of functional groups of molecules. It can be either organic or inorganic based on different groups or the different type of bonds or the way in the structure it is being defined. We can identify it from. Now in infrared spectroscopy we will get the image from a IR spectrum, which is a graph plotted between infrared light which is being absorbed as y-axis against frequency or wavelength. In some cases it is defined based on wave number, which is a number which has been derived from frequencies. Now IR spectroscopy dictates frequency of infrared lights that are absorbed by a molecule. So as I have already explained, the molecules may be absorbing certain range of infrared lights, and by studying how much amount of energy is being absorbed by the molecule, we can identify what type of molecule it is. So the molecules tend to absorb this specific frequency of light since they correspond to frequency of vibration of bond in the molecule. For a particular molecule you will be having a certain frequency vibration, and the electromagnetic lights which comes with the same frequency will be absorbed by the molecules. The energy required to excite the bond belonging to a molecule and to make them vibrate with more amplitude with the help of this infrared waves. Now a bond will only interact with electromagnetic infrared radiation which are of the same frequency as that of vibration of the bonds. The presence of separate areas of positive and negative charges in molecules allow electric field components of the electromagnetic waves to excite the vibration energy of the molecule. The change in vibration energy leads to another corresponding change in dipole moment of the given molecule. So the intensity of absorption depends on polarity of the bonds. For symmetrical non-polar bonds in, for example, N triple bond N and oxygen double bond oxygen do not disturb the radiation. In such cases, the interaction of electric field will not be influencing the spectrum. So you can see spectroscopy. It's usually being used in mid-range. Mid-infrared range is the energy enough for exciting the molecular vibration. We are usually using that. The wave of infrared absorption bands are characteristics of specific type of chemical bonds, and infrared spectroscopy finds its greatest utility for identifying different classes of organic and organometallic molecules. The high selectivity of method makes it useful for complex matrices. Now, by examining how much twist and bend, rotation and vibration motions occurs for atoms in a molecule, we can find it using infrared spectroscopy. Now, how we can obtain an infrared spectrum consideration? In infrared, for that we will be using an instrument called as infrared spectrophotometer, which is an instrument that passes infrared light through an organic molecule or inorganic molecule and produces spectrum that contains a plot between amount of light that is being transmitted. Either it may be based on transmission or it may be based on the absorption. On the y-axis against, it may be either wavelength or wave number, or it may be based on frequency on the x-axis. Now this spectrum, say if I am taking the y-axis, if it is transmittance as seen in figure given here. So here you can see in y-axis it is percentage of transmittance. So the percentage is been starting from 0 to 100%. Here you can see transmittance. Initially the transmittance is 100% transmittance happens corresponding to different wave numbers, but at a certain range it suddenly the transmittance reduces to a certain value at a wave number of 3078. That means at that corresponding infrared radiations, some of the energy is being absorbed. So the wave number and the intensity will be defining, or the absorption rate will be defining which corresponding chemical bond comes. So for example here 3078 will be defining the wave number 3078 with the transmittance about 80% will define that the corresponding molecule is CH stretch aromatic bond. Similar to that, if you take the next case, then after a certain period the transmittance is again decreased. That means inversely if I say the corresponding absorbance of the energy is being increased. So corresponding to different numbers and different intensities, you will be having different molecular bonds which is been defined. So here you can see SH stretch alkali is been defined by this wave number. Then the next one you will get CO stretch bonds, double bond, CO stretch single bond. Like that you will get for different wave numbers and different transmittance rate, you will be defining different molecules, and combining this you will get the molecule, the compound on which we are doing this spectroscopical technique. So from evaluating the IR spectrum we can understand what the chemical composition of the system is. So absorption of radiation lowers the percentage of transmittance. In some of the diagram it may be just the reverse. So usually the infrared spectroscopical figure will be defining based on percentage of transmittance. So that usually the figure will be taken like this. In some cases the peak may be just the reverse. It may be rising there. The y-axis may be absorbance based on the type of spectrophotometer being used. Okay, next we will be going through an important spectroscopical technique called as Raman spectroscopy. Here in the previous case we have taken absorption property. Next we are going to take into consideration the scattering property of a molecule. The electromagnetic waves when interacts with a matter, some of the electromagnetic lights are being scattered, and the scattering, the way in which the scattering distribution comes will be helping you to identify what will be the chemical composition. So Raman spectroscopy is a non-destructive chemical analysis technique which provides detailed information about chemical structure, phase, polymorphy, what is the crystallinity and how the molecular interaction happens. So it based on the interaction of light will be based on the chemical bond within the material. So here we will explain how position or how the scattering happens. In this case, if you take Raman spectroscopy light scattering technique where the molecule scatters incident light from a higher intensity laser beams. Now, how the scattering happens? A high intensity laser beams with certain energy and with certain frequency will be coming and uh, interacting with the molecules, and when the interaction happens, most of the molecules will be emitting out light of the same frequency or same energy. So such type of scattered light are called as Rayleigh scattered. It is mainly due to the elastic scattering. It is mainly due to the elastic scattering of the light. So incident light will be coming and interacting with the molecule, and you will be having elastic scattering, due to which you will be having Rayleigh's scattering light. But there is a small percentage of light which is scattered with different wavelengths of frequencies other than the incident light. That is mainly due to the inelastic scattering of light. So such scattered light are called as Raman scattered light. So there are two different possibilities. Either the frequency can be higher, or either the frequency of the scattered light may be less. So such scattered light are called as Raman scatter. So here you can see how we will be evaluating this. A Raman spectrum will be consisting of number of peaks which defines, it's similar to what we learned in the previous case. In IR spectrum, we defined it based on the absorbance or transmittance. Here we will be defining with respect to the different spectrums or scattered light frequency with respect to which it has been absorbed, the intensity with respect to which it has been created. So that has been defined in Raman spectrum. In Raman spectrum it features number of peaks showing intensity and wave position of Raman scattered light. So it's actually each peak corresponds to specific molecular bond vibration similar to the previous case, including individual bonds such as carbon-carbon or carbon-carbon double bond, carbon-oxygen, carbon-hydrogen, etc. There are a number of different functional groups can be defined based on the peaks. So from the peaks and the intensity, intensity and the wavelength, you can understand what is the corresponding chemical composition. Now, what is the basic working principle behind it? So here you will be having a monochromatic beam of light which is impinged on a sample, and a spectrum of scattered light is being examined. So due to the interaction of the laser beams, monochromatic laser beams with respect to the matter, a spectrum of scattered light will be obtained. The majority of them in this Raman spectrum, if you see at a corresponding wavelength, you will be having a very high intensity peak. Usually that very high intensity peak will be defining the frequency at which the frequency of the high intensity peak will be usually of the same as that of incident radiation. The reason behind that will be the majority of scattered light is coming in under that region, so the intensity at that region will be very high. So among the scattered light, the elastically scattered light dominates the spectrum with a high intensity peak, which defines the energy of the incoming photons. Now here actually we are not studying Rayleigh scattered light. Instead of that, we are studying the inelastically scattered lights, that is Raman scattered light. We are studying that. So the additional peaks that are observed at different energy stages, that is due to different excitation energy, are called as Raman peaks. We are actually studying this Raman peaks. In some of the graphs, it's actually Raman spectrum is a plot between intensity and frequency. Sometimes it may be based on Raman shift frequencies. Raman shift frequency means it's the difference between the frequency of incident ray and the frequency of incident ray and the frequency of the Raman scattered light. The difference between them is been defined as the Raman shift and based on that we will be obtaining different peaks. So here we are actually studying only the diamond scattered light. So the frequency of that one will be entirely different from that of incident light or incident electromagnetic radiation, and comparing with the difference between that is being studied, and based on that different intensities, different peaks at certain energy difference, you will be having certain higher peaks. So based on the peaks and the diamond shift values, you can understand what the chemical composition. So the shift in frequency, we will study what is the basic working principle behind it. The shift in frequency of light is due to interaction of photons of light with phonons. Phonons of light with phonons arise by vibration and rotation of molecules, similar to the previous case. Now if the interaction shifts the frequency of scattered photon to a higher frequency, then it is called anti-Stokes. And if the interaction shifts the frequency of scattered photon to a lower frequency, then it is called Stokes process. We'll go in detail on how it works. So here you can see an excited laser beam will be coming and incidentally interacting with the sample molecule, and due to that some scattered lights come out, and from there you will be studying, you will be having both Rayleigh's scattered light as well as Raman scattered light. By using transmission grating, we will be removing the presence of Rayleigh scattering and we will be taking only the Raman scattered lights, and using that we will be defining based on different wavelengths. We will be obtaining the Raman scattered light with different wavelengths, and we will be defining its intensity at different wavelengths, and that is being defined as the diamond spectrum. So here you can see the difference between both the case. The intensity for Rayleigh scattering will be very high, the frequency of that one will be same as that of the incident frequency, but if the scattered frequency is greater than incident frequency, then it is called as anti-Stokes, and the process is called as anti-Stokes process. And if the scattered light is having frequency lesser than that of incident frequency, then it is called as, this spectrum is called as Stokes line, and the process is called as Stokes process. We will go in detail on how the Stokes process comes and how the different scattering methods come up. Now here this diagram schematically defines how the energy excitation, how the particle moves or electrons moves from one stage to another stage. So this one defines different energy states. Say for example, let the electron be at a lower energy state, and when monochromatic laser beams comes and interacts on this one, at that time what happens, it is being excited to a higher energy state. Okay, electron is excited to a higher energy state. Now after some time the electrons will be decaying and will be coming to lower energy state. If this electron is coming back to the same lower energy state, then corresponding to that an electromagnetic radiation will be coming out with the energy equal to the difference between the two energy states, which is the same as that of initial case. That is the incident energy and the scattered energy, scattered light's energy, both will be same. So that corresponding condition is called as Rayleigh's scattering. So the majority of the electrons will be taking up this type of process. So that's why the majority of scattering that happens is Rayleigh scattering. But there are exceptions. There are exceptions where the same electron, say for example with the same energy, it can be excited to a higher energy state, and from there electrons will be decaying, but it will be coming back to a lower energy state. Say for example here it is defined as 1, which is a higher energy state compared to the first stage. So here you can see the energy utilized for going from lower energy state to higher energy state is like this, and from here, from higher energy state to lower energy state, it will be coming to a energy state which is higher than that of the first stage. So the frequency of the light that is being emitted will be having comparatively less value, because the energy difference between both is comparatively less. So here a low frequency wave will be excited out. This will be a certain number of electrons will be acting like this. So corresponding to that you will get a corresponding intensity for the corresponding wavelength. Similarly, just the reverse also can happen. That is, say for example, let the initial energy state, starting energy state of electron, let it be here. It is been excited to a higher energy state with some energy. Okay, when the electron is decaying back, it will be coming to a lower energy state, but in this case the electron takes up a position which is much more lower than that of the previous initial starting energy state. So in such cases, here you can see the energy difference between them will be greater than that of the incident light. So in such cases you will be emitting a high frequency or high energy electromagnetic waves. So as a sum, if you take the molecule as a sum, it will be combination of both the cases. So you will be having energy balance between both. Okay, and from there you will get different intensities for the spectrum depending upon the molecule, and by studying this spectrum you can understand what is the type of molecule being interacting with the electromagnet. Now we will study how the construction comes. It basically, the Raman spectrometer basically consists of three parts. First is a laser, which is a source of monochromatic light. Then you will be having a collecting device where the data from the interaction will be collected by the collection device, and then a spectrograph which will be converting the data obtained into a useful output form. So first element comes is laser, which is used to excite the Raman spectrum. So you will be having a monochromatic light which will be incident on the matter which you take or the specimen that you take into consideration, and the specialty of this one will be a high intensity electromagnetic waves will be given. The intensity will be sufficient enough to produce useful amount of Raman scattering, because the intensity of Raman scattering is comparatively less compared to Rayleigh scattering. So in order to get enough Raman scattering, you must give high intensity monochromatic laser beams. So we must be providing high intensity laser beams for this process, and it will be exhibiting good wavelength stability and low background emissions without any energy loss. With the same energy intensity we will be giving the laser beams. So that will be the main function of laser source, and from the laser source it will be interacting with the specimen which you take. And the next component comes is usually in the form of a probe. The probe is a collector device that collects the scattered photons, and this photons will be this scattered photon will be collected, and from here you will be removing the Rayleigh scattering. As I already explained, it will be removing the Rayleigh scattering by taking the intensity of spectrum which is having the same wavelength as that of incident photons, and then you will get the Raman spectrum, and this Raman spectrum is being passed on to spectrography. This in spectrograph what actually happens is we will be using a transmission grating which will be defining different intensities for different wavelengths. We will be splitting the Raman spectrum for different wavelengths, and we will be understanding what is the intensity of different wavelengths comes, and that is being recorded, and it will be converted into the required output form in the data acquisition system. So this is how the Raman spectroscopy works, and basic working principle and construction behind it. So with this we'll conclude. Thank you.